Interrupts are a very useful feature of microcontrollers. We're going to examine several different aspects of interrupts. First of all, compare the operation of microcontrollers when they're in polling or when they're in interrupts. Then look at some steps in executing an interrupt. We're going to look in depth at interrupts that come from external sources, so we'll examine external trigger versus level triggers in external interrupts. Interrupt priority is an important topic, and then look at what happens if an interrupt is generated during another interrupt. And finally, the presentation will show an example of a C program that uses interrupts. Microcontrollers can service many different subsystems, and whenever the subsystem needs attention from the microcontroller, it can get service in one of two ways. Let me start over here with interrupts. Interrupt method would mean the subsystem would send a message to the microcontroller. The microcontroller would immediately stop what it's doing and deal with that subsystem. So it executes some special code to happen in the event of the subsystem needing service. The other way that the subsystems can be handled would be what's called polling. And polling is where the program that the microcontroller executes goes through in a round-robin fashion and checks each of the subsystems to see if they need service. And if one of those subsystems has met a certain predefined condition, then that service is given to that subsystem. So here is an example of polling. We have the while loop that goes forever that the microcontroller executes. Inside that loop there is a check to see if some condition is met, and if that condition is met, then we'll execute specific code or special code for that subsystem. And then we would go on and check the next one and the next one. Here's an example of pseudocode for interrupts. We have main, and then we have, this would be where we're doing our repeated code. So whatever operation the microcontroller executes in normal operation. And then there will be code outside of main that's handled whenever an interrupt request is generated. And we'll look at all of these topics for interrupts a little bit later. But there are a few important benefits to using interrupts. First of all, interrupts can be masked, and what's meant by that is basically the interrupts can be enabled or disabled. So we could handle interrupts or decide to ignore interrupts, and that decision, that masking, can be set within the program. Interrupts, another advantage is that interrupts have priority. That means that if, for example, we had external interrupts from, say, a kill switch and one to reverse the direction of a motor in some certain application, we might want the kill switch to be treated first if both those buttons are pressed at the same time. So interrupts have priority inherently. And then finally, efficient CPU use is probably the biggest benefit of using interrupts. So for polling, the CPU has to go check all the conditions while it could be doing something else, whereas if you're using interrupts, then the CPU does its normal operation and only deals with the interrupts whenever they're generated. There are several different sources for interrupts in the microcontroller, and we'll look at a few of them today, or in this video. But specifically, we want to consider interrupts from timers and also interrupts from external triggers, external sources. In order to handle interrupts from any source, the I bit for an Atmel microcontroller needs to be set. And that I bit is in the status register, special function register, so it's bit 7. And if this is 1, then interrupts can be handled from various sources. If it's 0, then no interrupt from any source can be handled. There's a simple command to set this. It's SEI, and then to clear it, it's CLI. Once this bit has been set, then the microcontroller will treat other interrupts if they're enabled, and those are enabled individually. But they're enabled by the same method, which is to set specific bits in special function registers to 1. For example, here for the AT Mega 32 is the TIMSK register, which is the timer mask register, and this enables interrupts from the 3 different timers. So here are 2 interrupts from timer 0, 4 interrupts from timer 1, and 2 interrupts from timer 2, and we can enable all of these different types of interrupts. For the AT Mega 32, we also have interrupts for the external interrupts, INT 0, 1, and 2. And these have to be set to 1 in order for the microcontroller to handle interrupts from those sources. Whenever an interrupt request is generated, that means that a specific bit has been set. It's called an interrupt flag. So for example, we have here in the AT Mega 32 the timer interrupt flag register. This is where all the flags are stored for the different timers. Now say we had set the I bit, so we enabled interrupts globally, and we set TIMSK bit 7, so the output compare interrupts were enabled from timer 2. Then whenever timer 2 sets this flag, which by the way stands for output compare flag 2, then an interrupt would be generated. And execution on the normal program would pause, and we would go to what's called an interrupt service routine, or ISR, specific to this source. So the ISR for the output compare interrupt, output compare for timer 2 would be executed. Yes, I know that's a lot of material to handle, but the overall concept is that you have to enable interrupts, and they can be generated from various sources. Now let's look at the external interrupts. Here's a pin diagram for the Mega 32. You can see that there are 3 external interrupt pins, INT 0, 1, and 2. So they're at PD2, PD3, and PB2. And in order to use interrupts from any of those, we have to enable interrupts. Now, interrupts can be requested from these pins in different conditions. So that means different scenarios for the voltage on these pins, and we'll look at that soon. Every microcontroller is going to have an interrupt vector table, and this is used to direct execution to specific places in memory. And the important point of this table for our context is just that each interrupt service routine has a different place in memory. So depending on what source generates the interrupt request, program execution is going to go to a different place in memory and execute different code. So you can see there's a place in memory for external interrupt 0, external interrupt 2, analog to digital conversion can generate an interrupt, serial transmission can generate interrupts, timers, like I said, have at least 2 interrupts each. But again, there's specific interrupt service routine code for each different interrupt source. Now, for the external interrupts, they can be generated in different cases, different scenarios. For the AT Mega 32, the configuration register for these external interrupts, that is the register that determines what scenarios generate interrupts, is called MCUR, and there are just 2 bits in that register to configure interrupts from INT 0. 2 bits for INT 1 and then another register for INT 2. So let's look at interrupts from INT 0. If these 2 bits, the 2 least significant bits of MCUCR, are both 0, which is the default, then whenever the INT 0 pin is low, an interrupt request is generated. So it goes low, an interrupt request is generated, execution pauses on the main program, the interrupt service routine is executed for INT 0, and when that's done, execution returns to the main program. If INT 0 is still low, then it will immediately jump back to the interrupt service routine. So that's what's meant by the level trigger. The other way of handling it would be the edge trigger. So this generates an interrupt request only whenever the voltage on INT 0 changes. If we want it to generate an interrupt request for any change, that is high to low or low to high, then we'll set these 2 bits to 0 and 1. So ISC 01 is 0 and ISC 00 is 1. If we want interrupts to be generated when the voltage goes from high to low, we'll set bit 1 to 1 and bit 0 to 0 according to this table. And if we want interrupts to be generated when the voltage goes from low to high, we'll set both these two least significant bits of the MCUCR register to 1. INT2 only has two configurations, or two possibilities. It does not have level trigger. It only has edge trigger for falling edge and for rising edge. So there's only one bit that controls that configuration. Interrupt priority is determined by the location, the memory address in the interrupt vector table. Interrupts with a lower address have higher priority. So if we have buttons connected to INT0 and INT2 and they're pressed at the same time, then the interrupt for INT0 is going to be handled because it has higher priority. And you can refer to the vector table to see which has the higher priority. And that brings up the thought of interrupts inside an interrupt. So what happens then if we're inside an interrupt service routine and another interrupt request is generated? Well, that's easy to answer because the microcontroller calls CLI whenever it enters an interrupt service routine. And what happens when CLI is called? The I bit is reset, or it's cleared. And what happens, what is the effect of clearing the I bit in the status register? Interrupts are disabled globally. So whenever the microcontroller enters an ISR, the I bit is cleared, so all interrupts are disabled. So no other interrupts can be generated until the microcontroller finishes the interrupt service routine it's executing, at which time it will set the I bit in the SREG special function register, thus re-enabling interrupts globally. The final slide shows an example of a program written in C, and the operation of this program is to toggle the voltage on port C pin 3 whenever a button that's connected to the INT0 pin is pressed. Or no, not when it's pressed, but whenever it's low. So as long as it's low, the microcontroller is just going to toggle the voltage on port C pin 3. So that button connects the INT0 pin to ground. So we want to enable the internal pull-up resistor on that pin. And let's go back a few slides to the pin diagram for the ATmega32, which is the microcontroller that this program is written for, and look and see which pin INT0 is. There it is. INT0 is port D pin 2. So now we know we need to enable the internal pull-up resistor on port D pin 2 because we're going to use INT0, the external interrupt. You see we have an include for the I/O library as well as the interrupt library. We'll look at why in just a second. The first line of our code, DDRC, we are going to assign a 1 to bit 3 of data direction register C. So that makes port C pin 3 an output. Then the next line we will assign a 1 to bit 2 of the port D register, and that enables the internal pull-up resistor for port D pin 2. The reason it does that is because DDRD is all zeros by default, and so it's an input pin. And so when we write a 1 to this register for that bit, that enables the internal pull-up resistor. Now we are going to enable interrupts for INT0. And this syntax here, INT0, is defined in a macro that's in the interrupt library. So the compiler is going to interpret INT0. It's going to replace that with the number for the bit in the GICR register. So let's look up just to see what I mean by that. Where was that GICR register? Okay, here it is. And you can see that INT0 for this microcontroller is bit 6. So when the compiler sees INT0, it's going to replace that with a 6, and that's defined in the interrupt library. So what we're doing is assigning a 1 to bit 6 of the GICR register, and that enables external interrupt 0. The next line is SEI, and this assigns a 1 to the I bit of the status register. So now interrupts are enabled globally, and this interrupt is enabled. So for this example, the microcontroller is just going to pause. Whenever the voltage on port D pin 2, more specifically the INT0 pin, is low, then execution will move from main to the ISR, the interrupt service routine. And the name of this is specified, so we can only, so this is the syntax for writing an interrupt service routine. We have ISR and then in parentheses the name of the vector. And the name of the vector sort of follows the pattern. You have the vector source underscore vect. So for this one we have INT0 underscore vect. And if we wanted to use the INT2 pin, then this would change to ISR parentheses INT2 underscore vect. But as it stands now, whenever the voltage on the INT0 pin is low, then we're going to perform a bitwise exclusive OR with port C and 1 left shifted 3. So we're going to toggle the voltage on port C pin 3 as long as INT0 pin is low. And the reason it's as long as INT0 pin is low is because by default these two bits are zeros, and so the interrupt is set up for low level interrupt request.